Now talk about limits, which plays a key role in calculus. So when we talk about limits, what we are talking about is a limit of a function. Of course, you could think of a function like an equation. So the way you write a limit, sort of use cursive script. And let me write out an example of a limit, and then I'll define it. So how you would say this, you would say the limit as x approaches 5 of f of x. The limit as x approaches 5 of f of x. The key here is the word approaches. We are not going to evaluate the function at f equals 5. If we wanted to do that, we would write this, f of 5. Instead, we're saying what does the function equal as x approaches or gets close to the number 5. And the reason we do this is oftentimes we will have functions that if you put the actual number in the function, you get an undefined number, and you can't really use that. But instead, we have this idea of a limit. And as we go into this, this will be more clear what I'm saying, if it right now seems a little fuzzy what I'm trying to say. So a natural question might be, what's the purpose of limits and why do we use limits? Now really, in these next couple of videos that I'm going to prepare, in my mind, I'm going to look at two different kinds of limits. The first kind is when you have a limit of the function and the limit is going to approach a number. Like this example I wrote here, the limit as x approaches 5 of f of x. So we're going to talk and do some examples of where you take the limit as x approaches some number. Could be 0, could be 1, could be 5, could be negative 10. All right. But then there's a second kind of limit we're going to look at. And it becomes special because the number it approaches is going to be infinity. Sometimes you'll have a function and you want to determine what the function is going to equal when x gets to be really, really large or huge. Well, the way we express that in math is to say as x approaches infinity. You know, you could think of taking your function and setting x equal to 1,000,000 or 1,000,000,000. And then look at the function and see what the function would equal when x gets large. There are also sometimes problems where you might look at the limit as x approaches, you see the little negative here? This indicates negative infinity. So this would be like a huge negative number, like negative 1,000,000. Now these are both limit problems, but they're in one sense very different. And actually, the limit as x approaches a number becomes important as we try and begin to look at how calculus works. The limit as x approaches infinity is important in math, but it's not just, we don't need to go through this in order to start working through calculus. This first kind of limit is the foundation of a big part of calculus. The limit as x approaches infinity is just important mathematically, but not essential for calculus. But we're just going to go ahead and cover both of these since we are going to talk about limits. But we're going to cover number 1 first, and then after we talk about finding the limit as x approaches a number, then we'll go in and talk about what happens when x approaches infinity. Now, why is this first kind of limit important for calculus? Well, later on, actually pretty soon, one of the first big ideas, principles of calculus is finding what's called the derivative. Now, I'm just going to write the basic definition of the derivative. And in this case, the derivative uses a thing called oftentimes called the difference function. So the derivative is defined as, I'm just going to write this and I'm not even going to necessarily explain it, and it won't even really make sense. We'll talk about this in a few lectures from now. But the reason why we even take the time to try and understand limits is because of this definition. The derivative is the limit as h approaches 0. H is a special variable we like to use when we talk about derivatives. F of x plus h minus f of x all over h. This right here is called the difference function, I guess because we're subtracting. And this is function notation. This is sort of messy, but this is the actual definition of the derivative, which is one of the key principles in calculus. Now the whole point is, look at what we have here. We have two functions in the top of this fraction, but look at what's in the bottom of the fraction. We have this variable h. And this is saying take the limit as h approaches 0. What would happen if we just took this expression here and set h equal to 0? Well, you can't divide by 0. So this would be undefined. So it would be meaningless. It would serve no purpose. But in the idea of calculus, we're going to see later on the derivative. In order to get the derivative, h has to be very, 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 very small. As a matter of fact, what we say is we want h to approach 0. It never, ever gets to 0, because if it ever gets to 0, all of a sudden we have a 0 in the denominator. But we do want h to get as close to 0 as possible. And that's what a limit does. The limit says, hey, as h gets really, really, really close to 0, what does this equal? The derivative is really the first thing we're going to do in calculus, and it's almost like the foundation of calculus. And the way we calculate the derivative, the principle of the derivative, involves a limit as h approaches 0. So this is just why we have to take some time to talk about limits. And to be honest, we're going to solve some problems where we use this definition, and it's going to be sort of tedious and sort of painful. And then after that, we're going to learn some rules about derivatives, and you won't really use this definition very much. But sometimes in math, it's important to know the principles involved in getting from A to B, even though you don't always have to use it to solve ordinary problems. So that's how it is with limits. I'm not saying we're going to be using limits all the time, but it is one of the foundational principles that are needed to start working with calculus. And you're going to find out understanding limits is not that hard. So let's just go ahead and dive in. Now, as we talk about limits, just to help your understanding, I like to illustrate it in two methods. First, we're going to look at graphs of functions. And by looking at graphs of functions, it's just old-fashioned, here's a function. We're going to look at some graphs of functions and see how to calculate limits from looking at graphs. And then we'll go ahead and begin to figure out how to determine the limits when we're given an equation. So this is more sort of using math to find limits, and this will be looking at graphs. So let's go ahead. I have prepared here, I have drawn 4 functions on the same page. The function looks sort of alike in some ways, but they're all a little bit different. So you can sort of see they all are similar in one ways, but there's minor differences, and that's going to be important. So what I want to do is I want to look at each one of these, and I'm going to figure out 4 separate things about each of these graphs. Now let's remind about graphing. Here I have a nice smooth line, curved line, and when x is 3, I mark this point here. So the y is like my function. So here's my function. When x is 3, I'm looking right here. Even though I drew this point here, this is just a nice continuous line. Now if I go to this second graph, the only difference is, remember in graphing, when you have an empty circle, that means you skip. There's no graph at this point. So here, the graph is continuous and all connected here. Once you get to 3, it's like you have to skip x equals 3, then you keep going. So the only difference between these first 2 graphs is, on this graph, the function is not defined when x is 3. When x is 3, there's no graph there. It's undefined. Now we go to the third graph, and it's very similar to the second graph, except you know what they decided to do here is, as you're going along on the graph, the same thing happens when x gets to 3. It's undefined, but then they decide to go ahead and give a value when x is 3, except the value's not as part of the line. They decide just to put the point down here. So for this graph, you say, what is the function when x equals 3? You would say 2. And then finally, the fourth graph, which is sort of unique, the other 3. The graph starts out the same. It sort of goes up here. It gets to x equals 3, once again an empty circle. But instead of then continuing on, this one, it jumps down sort of to like this point here, and then it continues on. So I guess the key thing I want you to realize as we look at these is this first one is a continuous graph. Every point's defined, no gaps, no breaks, no jumps. Here we have a gap when x is 3. Matter of fact, the function does not exist when x equals 3. Here we have a gap in our graph when x is 3. But in this case, the function is actually defined. When x equals 3, the function goes down here, so the function does exist at x equals 3, but it's just not a part of this line. And then here, we're going along, and then it's when x is equals 3, all of a sudden, like the whole graph has a big gap, and then it keeps going. So that's the 4 graphs. Now let's analyze looking at limits of these graphs. Although the first thing actually I'm going to look at is not a limit. For each of these graphs, the first thing I want to determine is what is the function, what's the value of the function when x is equals 3. Okay, so when x equals 3, it's this point right here. What's the value of the function? It looks like it's 3. Now I'm going to do the same thing for all 4 graphs, but let me do the 4 things I'm looking for my first graph, and then I'll do them for the second, third, and fourth. The next thing I want to do is, now I haven't really talked about this yet. Let me write it, and then we'll talk about it. The limit as x approaches 3, however, you know, when you talk about as x approaches 3, the idea is you're moving along the function, the graph, the line, and you're seeing what is the function equal to as you get close to x. But the interesting thing is I can move like this. I can approach x equals 3 from here. But you know what? Why could I not go over here and approach x equals 3 from the right side? I mean, what should I, when you look at a limit, do you approach it from what we call the low side, because the numbers here are smaller or lower than 3, or should you approach it, I mean, you can come at it from either side and you're still approaching x equals 3. What should you do? Well, what we do is, when we want to distinguish how we approach the point, we put a little sign here. So this is going to be the limit as x approaches 3, and this means from like the negative side, or you could think of from the low side. Right, because negative x is over here, so we think of this as like the negative side of the graph. So this is like what? So as I get closer and closer, as x gets closer and closer to 3, and I'm coming from the low side, what is the function going to be equal to? Here's how I write that. So the limit as x approaches 3 from the low side of f of x is what? Well, this one seems, it's actually going to be 3, right? What's the value of the function? What's the value of y as I get close to this point? It's 3. And just for fun, now this graph is not the most interesting, but I'm going to do the same thing, except now I'm going to look at the limit as I approach it from the high side, or the positive side of the graph. So now, so if I want to, this is how you approach it from the positive, this is how you approach it from the negative. So over here, the limit as x approaches 3, as x gets closer and closer to 3, what's my function going to be? It's also going to be 3. I probably should have made these numbers different. Some of you might be confused. But anyways. And then there's one more. So in this case, I've done the limit as x approaches 3 from the low side and the high side. But what happens with limits is, as you look at a limit from the low side and you look at the limit from the high side, if those two limits approach the same number, the same function, the same value, then you actually have a limit. So I say the limit as x approaches 3. I look at the low side, it's 3. The high side is 3. Since these are the same, what I can say is, hey, the limit as x approaches 3 of f of x equals 3. Now that has to be true. For a limit to exist at a point, you have to be able to approach it from the high side and the low side, and they have to approach the same point, the same value of the function. As we do these other examples, you'll see. So here are the 4 things I'm going to look at for each graph. What is the function when x is 3? What's the limit as x approaches 3 from the low side of the function? What's the limit as x approaches 3 from the high side of the function? And based upon what I find here, what's the limit as x approaches 3 of the function? And once again, since the limits from the low side and the high side approach the same, have the same value. So let's look at this second graph. First question, what does the function equal when x is 3? Well, when x is 3, it's this point right here. And you know what? That empty circle means it's not defined. There is no function there. Undefined. The function does not exist when x equals 3. However, what about the limit as x approaches 3? The limit of the function as x approaches 3 from the low side. So now I'm going here, x is getting closer and closer to 3. What is the function as I get closer and closer to x equals 3? Well, once again, my function over here is 3, and as I get really close to x equals 3, I'm getting really close to the function equaling 3. And that's what a limit says. The limit says not, the limit doesn't ask what's going on when x is 3. The limit says what's happening when you get really, really, really close to 3. So in this case, as I get really close to x equals 3, what is my function getting close to? 3. And if I look at the same thing coming from the positive or high side, so as I'm going here and as I'm getting closer and closer to 3, as x gets closer and closer to 3, what is my function getting close to? Once again, 3. And so the rule is, if you're trying to figure out whether the limit exists at a certain value of x, you look at the limit from the low side and the high side, and if they approach the same number, then that becomes your limit. So really, between these first 2 graphs, the only difference is the actual function. Here, at f of 3, the function exists, it's just 3, but here, it doesn't exist. But you know what? Both of these graphs have the same limit. Because the key idea of a limit is not what is the value at that value of x, what's the function at that value of x. The key to a limit is what is the function as we approach a certain value for x. And the limits of these two are the same. How about this one, this third one? Let's figure out the same 4 things. Now for this one, what is f of 3? So what's the function equal when x is 3? Well, the graph is up here. There's an empty spot here, but turns out there's a dot here. It looks like when x is 3, my function is 2. In other words, this function sort of like goes along this line, goes along here, goes along here, and as soon as the function gets to x equal 3, it jumps down here just for 1 point, and then as I keep moving to the right, it jumps back up, and it keeps going. So then the question is, so what is the function when x is 3? When x is 3, the function jumps down to here. The function's 2. Well, how about the limit? From the low side as x approaches 3. So once again, we're moving to the right. We're getting closer and closer to where x is equal to 3. Once again, I don't really care what happens when x is exactly 3. What I care about is what is my function approaching as I get close to 3. And once again, when you come from the low side, the function is approaching 3. And what happens when you approach x equals 3 from the high side? You go like this. Once again, as x gets closer and closer to 3, what's happening to my function? My function's getting closer and closer to 3 also. So now, when I ask, okay, so what's the limit as x approaches 3? Well, because the limit from the low side and the limit from the high side are the same, then I say the limit as x approaches 3 is 3. Okay, last one. Same 4 things to figure out. What would f of 3 be here? Once again, here's our graph. When x gets to 3, it's not defined here, but it jumps down here. So it looks like, once again, f of 3 is going to be 2. Now let's look at our high and low limits as x approaches 3. So here, from the low side, as x approaches 3, what is my function approaching? 3. How about as x approaches 3 from the high side? Now look here, as x approaches 3, what's my function approaching? It's actually approaching 2. So now when we're asked, okay, so what's the limit of this function as x approaches 3? Well, remember, for the limit to exist at a certain value of x, when you approach the value of x from the low side and the high side, they have to be approaching the same value for the function. But when I approach it from the low side, the limit is 3, my function is 3. When I come from the high side, it's 2. Since these are not the same, we say there is no limit. It's undefined, which you can see from the picture. All right, so hopefully this little exercise helps you to sort of visualize what we're doing when we talk about these limits. The limits are, as you approach a certain value of x, what is the function approaching? You notice in this example, the function doesn't even exist at x equals 3. And in this example, it's like the point is off by itself, and this one looks like there's a big jump in the graph. So for these two, the limits still exist because both sides of the graph are approaching the same point, but here they end up approaching different points, so there's no limit at all. Alright, so let me stop now, and then what we do in the next video is we're going to actually start talking about how to evaluate limits mathematically. So if we're given a function written as an equation, how do we determine the limit?